In the second segment of our lecture on quantification, we're going to focus on one kind of quantification called universal quantification, which shows up in English in sentences like this one. So let's assume you have a predicate or property P that you're interested in, and you want to state the fact that every object in the universe has that property P. In other words, for all values of x in the universe, P of x is true. The quantified expression you would use in predicate logic to represent this sentence is the following: for all x, P of x, where, as we saw before, these symbols represent universal quantification. Now, every quantifier has a scope. Now, in this case, I did not use parentheses around the expression that's quantified because it's a single proposition, P of x. It cannot be decomposed into smaller propositions. In a way, it's an atomic proposition of predicate logic. But just to be clear, I'm going to add the parentheses anyway to make the scope of the quantifier explicit. So this is a second way of representing the same sentence, namely this one. So, in a nutshell, this is what we call universal quantification, and every time you want to take an expression like P of x, or it could be any arbitrarily complex expression with one or more predicates, and you want to quantify it in a universal way, you just precede it with the for all quantifier followed by whatever variable you want to quantify over. So for all x, P of x, as we just argued, is a proposition. In other words, it's either true or false. So let's focus on the situation where that proposition is true. But what does it mean for all x, P of x to be true? Well, here is the definition. For all x, P of x is true if and only if P of x is true for every element in the universe of x. So what does that mean more specifically? Well, let's assume for a moment that the universe is a finite set comprised of the elements, for example, x1, x2, all the way up to xn. Then the proposition for all x, P of x is logically equivalent to a finite conjunction, namely P of x1 and P of x2 and and P of xn. So it's important for the universe to be finite, because if it wasn't finite, you would end up with an infinite conjunction over here, which is not something we are ready to deal with. But the important thing to notice here is this is really just a shortcut for a conjunction of n propositions, namely P of x1, P of x2, and so on. This is just a short or an abbreviated way of stating the fact that P of x holds for every single element in the universe U. Now remember, the definition of logical equivalence, which this symbol denotes, is simply the fact that this proposition of predicate logic and this other proposition of predicate logic are always true at the same time and false at the same time. They are logically equivalent. Now, since any proposition can be negated by inserting a negation in front of it, let's consider the negation of this for all x, P of x. And my question to you is, first of all, you should be convinced that this is a proposition. It's either true or false. But the question is, when is it true or when is it false? In other words, what is it equivalent to in logic? So there are at least a couple ways of answering this question. First, let's try to reason in English. If it's not the case that for all x, P of x, then it is not the case that the property P holds for every element of the universe. Therefore, there must exist at least one element in the universe for which P is false. In other words, for which not P is true. So finally, either not P of x1 or not P of x2 ... or not P of xn must be the case, since it's not the case that P of x is true for all of these elements. So in conclusion, we have these logical equivalence that we just arrived at. Now, of course, now that we have the answer, you might see a second way we could have used to solve this problem, and that's the following. Since all we did was put a negation here in front of the for all x P of x, we could have obtained a logically equivalent proposition by putting a negation in front of this one. And then it's a simple matter of applying De Morgan's laws to go from here to here. So it's possible that some of you, as they were trying to solve this problem, ended up with a different answer, like this one. And if you did that, an obvious way to get to that answer is to take the negation here that's in front of the proposition and to simply move it just in front of the predicate P. Now it turns out these two propositions are not logically equivalent. In other words, this is not the correct answer. So in case you did not realize that yet, that's okay. Just pause the video and think about why that is the case. Remember that a natural way of proving that two propositions are not logically equivalent is to find a counterexample, that is, a situation where one is true and the other one is false. And here it's not very hard to do. For example, let's pick for U the domain of the integers between 10 and 20, say. So x1 equals 10, x2 equals 11, ... xn equals 20. And let P denote the property of being a prime number. So in this interpretation, this proposition becomes, it is not true that every number in the domain is a prime number. And that is definitely the case, since the first element, namely 10, is not a prime number. So that just makes this proposition true. Now, what is the truth value of this proposition in this particular scenario? Well, what this proposition says is, for every element in the universe, it is not true that that number is prime. In other words, for every element in the universe is not prime, is what this says. Well, that's not true because, for example, x2 equals 11 is prime. So in that case, this proposition is false, but this one is true, so they're clearly not logically equivalent. So in general, the reason they are not logically equivalent is because they mean two different things. This one is saying it's not the case that P of x is true for every element in the universe, whereas this one says it is the case that for every element in the universe, P is false. Let's look at another example of universal quantification. For all x does not have to apply to a single atomic proposition like P of x. It can apply to any arbitrarily complex proposition like D of x implies M of x, although that's not quite a proposition, but let's not come back to that. So what we get as a result is for all x, D of x implies M of x. Now notice if you don't add parentheses, as I did earlier, to specify the scope of the quantifier, it is not very clear whether this x, as well as this one, both belong to the scope of this quantifier. So I strongly encourage you to add these parentheses here to make it clear. Now, a universally quantified proposition like this one often comes from the translation of an English sentence of this form. All D's are M's, where D and M are any two properties. So we're not concerned with the translation from English to logic anymore. In fact, let's focus on a different question, which is, how do we determine whether such a proposition is true or false? And in the remainder of this segment, we are going to develop a graphical way of representing these kind of situations. Now, since this proposition contains only one variable, we must consider one universe of possible values for x. Now, let's represent this universe with a rectangle containing each one of the possible values for x, shown here as a red dot. How are we going to represent the predicates d and m? Well, let's say the predicate m is a property of the objects in the universe, which means some objects will have the property and some will not. So one way to depict a predicate such as m is to indicate within the universe which of the elements have the property m. And we do so by drawing a circle around all of these instances or elements of the universe. So all the red dots within M are the only elements of the universe that have the property M. And every dot outside M do not have the property M. And this is how we will represent every predicate. Now, how should we draw the circle for the predicate D if we assume that this proposition is true? But before we do that, let's consider one of the elements of the universe that are not in M, like this one. Assume that d of x is true for this particular x. Then we would have a situation where d of x is true but m of x is false for a particular x in the universe. And so that would contradict the fact that this proposition is true. So in conclusion, for any element outside of the blue circle, it's impossible for d of x to be true. So in conclusion, the only way we can draw the circle for d of x is somewhere inside the circle for m, like this. So in conclusion, if this proposition is true, it means every element for which d is true must also belong to m. In other words, the circle for d, or the set of elements for which d is true, must be a subset of the set of the elements for which m is true. And so this graphical representation of one set inside of another inside of the universe is a pretty intuitive representation of the meaning for this particular universally quantified proposition.